Thank you very much for this opportunity to give me today to present you some nice piece of mathematics. I think that it somehow fitted the topic of conference, maybe not exactly, but you will see later maybe. So let me start from formulation what I will talking about. So my talk will be, as almost all talks here, about functions from RD, let's say real functions and differential operators. It means we define the collection of operators Tj, which will be of the form sum of the alpha of f, where the rank of partial derivatives here are fixed, let's say with some coefficient c alpha j. So we have the collection. We have I'm sorry.
Constant coefficients.
Constant, yes. So we have collection of differential operators of fixed order with constant coefficients. So a little bit more general theorem will be about the operators of more general form. So we replace here the order by the anisotropic order. So we have some collection, let's say gamma 1, gamma d of numbers, and we sum over, let's say, such an operators that sum of alpha j, gamma j, well, maybe this is wrong to use the j here and here, I equals 1 to d equals some number m, and this is the same form. Yeah? Okay, so when we fix such an anisotropic order, we will have the different type of theorem. So when we draw a simple picture which indicate where those partial derivatives lies on let's say ZD space, so we put the numbers alpha which are here in the sum on the space, so you will see immediately then here all those alphas lie on such a hyperplane. And the difference here is such that this is not hyperplane which is perpendicular to the vector 1, 1, 1, 1, 1, but just like that. Okay? So our question will be the following: whether we can estimate the norm T1 of f, let's say LP norm, by some fixed constant independent of anything, times the sum of the norm Tj from j equals, let's say, 2 to m. We have m such an operators of p. So whether for every function p, f, let's say from c infinity 0 or Rd, we have such an estimation with constant independent of anything here. So you will see that the answer depends very much on the number p. So first of all, you can see, for example, that where p equals 2, it is enough that symbols of those operators dominate the symbols on that operators. With another reflexive p, we have the similar situation. You just need to use a Michelin multiplier theorem to derive the boundedness of T1. So the interesting situation is where p equals infinite or p equals 1. So the easier situation, much easier, is when p equals infinity. And this was first done by, maybe not in very big generality, but by Boris Mityagin, probably already in the 50s, when he explicitly wrote down the formula for function which, let's say, Okay, his paper was about the partial derivatives. This was not polynomials, so he take a collection of partial derivatives of the same order and another one which is not in those collection, and he just wrote down the formula function which has the L infinity bounded derivative of the collection and has not for this exceptional operator. Then I think this was paper of Mirkil and Deleu. And those two prove the following theorem that, let's say, maybe to be simpler, that if we have such an estimation with independent constant, then T1 must be, let's say it that way, T1 must be just a combination of, let's say, alpha j times Tj from j equal to m. So inevitably, whenever we have the estimation of the norm, we have just a linear combination of other polynomials being, polynomials, operators. Sorry?
Does this linear combination imply the estimation of
Sure. This is okay. So the proof was relatively easy, and maybe this is, I have no time for repeat it, but let's say, because I will concentrate on the case p equals 1, which is definitely much more delicate, let's say, and also I put here the theorem, because this is the famous theorem of Ornstein. From the beginning of 60s, that the same actually holds for p equal 1. So what is the problem with Ornstein theorem? The problem is that his proof is extremely complicated. This is like tedious to read it. There's several indices, the family of function which is indices by 4 indices and something like that, very perpetual induction. So this was my purpose from several years before to understand why it is so. So finally, we get a solution and we get a proof which is so accessible that I take a risk to show you all those proofs here, and I expect that you will understand all the steps of my proof. Not my proof, this is joint, well, let me say some names here should be mentioned. So first of all, this is joint paper with Christian Kazaniecki, who is present here, and Dima Stolyarov from St. Petersburg. Moreover, some of the ideas which appear in this proof are taken from Brent Kirchheim and Jan Christensen. Moreover, if you are very, very curious, you can trace back even to the old paper of Ivanets, who used idea which was later developed by those guys. So definitely I need to credit those people here, and also, moreover, I had to say that they, parallel to us, they also gave a proof. However, ours is better because it's simpler. Maybe this is not a competition to give the difficult proof, because difficult already exists. So. Okay, so one more word about the proof. Our proof also has some novelty. Where is this? Has some novelty because we also are able to cover the case of mixed homogeneity, however, not totally. You will see there are some limitations, so this is another good thing about what I'm going to talk. I leave some open problems here, so I'm very happy to do. Okay, so after this introduction, I can pass to the proof. Let me, where is this? Okay. So we need some additional notation. Maybe before the notation, let me say that The formulation of the theorem is equivalent the following statement for some c bigger than 0, infimum over all function phi from c0 infinity on 0, 1 to the power d, sum of the norm tj of phi minus c norm t1 of phi equals 0, yeah? Okay, this could be easily achieved by phi equals phi being 0 function, and otherwise it's dominated. So this is equivalent to the statement of what we're going to do. So let me introduce something.
On the right is L1 for norm.
Yeah, sure. Probably all the norm today will be L1, so maybe I will forget. Not all. Or equivalent, because it will be some finite dimensional Hilbert space also, but yeah. So what is the generalized gradient? So suppose, maybe I go back for those operators here, maybe, we have the form of those operators here. So let's take the collection of all possible alpha, which, okay, let's say, remember Tj was the sum of C alpha j times the alpha. So let's take the collection of all possible alphas which appear in all those formulas for Tj. So this will be the multi-indices from the ZD. And we introduce the finite dimensional Hilbert space E, which is spanned by the unit versors E alpha, where alpha belongs to A. A is those set I mentioned before. So this will be, you see, the dimension of E equals the number of elements of the set A. Okay, and having this, we can define something which I call the generalized gradient. Maybe I put dot inside here of function phi. This is just, well, in this terminology, this will be the vector valued function d alpha of phi times E alpha, sum over alpha in the set A. So this is so from in any point x, this is pointwise expression. Now, you see, this was easy. Having the operators t, we can define the operators t tilde, t j tilde. Those will be the linear operators from E to E, given by the formula Tj of E is an element of E equals sum C alpha j E alpha. Those are just vectors. So it looks like diagonal operators in the Hilbert space.
Tj tilde acts on what?
On this Hilbert space. E is an element of E.
And where does E appear in the answer?
Okay, you're right. Probably you have to write this this way. Yeah.
Okay.
I mean, I tried to be too short. I'm sorry. So this is just the formal reading of this corresponds to the operator Tj. Yeah. So then we introduce the function v from E to R, which is just defined by v of E equals sum from j equal 2 to m t tilde of E, which is this is a norm in this Hilbert space for a moment minus c t1 tilde of E, and still another reformulation of another reformulation of what is written here will be just that the infimum over the same set of function, maybe I skip this, of v of the generalized gradient of phi of x the x, this is the this is the integration against the Lebesgue measure on RD, is equals 0. Okay, just did nothing at the moment. Okay, so maybe I will use the next blackboard. To do some more interesting stuff. So, the main idea of the proof begins from the definition of next function, which is when you can recognize kind of Bellman function here with what I read. This will be the following function b from E to R, given by the formula b of E equals infimum over all function phi from C0 infinity 0,1 to the power d, v of E plus those gradient, generalized gradient, dx. Okay, definition as definition. But why I introduce this function? So suppose for the moment that we already know that this function is non-negative. Okay, what follows from that? It follows that v is non-negative for every e. Why? Because this is infimum, so we can take zero function here, then it will be constant. The constant integrated by everything will be constant, and then this function is bigger than 0. So what follows from that? It follows that if you see for the definition of function that the kernel of the operator T1 must contain the intersection of kernels of operators Tj. So this is clear because, well, otherwise you take, where is this? Yeah? You can take something which is 0 everywhere here, and this is something from outside of this intersection, you could get negative number. And this is nothing but our statement, because this directly means that T1 equals sum of gamma j Tj. So there is the combination, let's say, is equal to m. So you will see that our purpose for now will be to prove that the function b is non-negative. Okay. So we start from the investigation of some of the properties. Let's say properties of b. So they are very simple. B of E is dominated up to some fixed constant by the norm of E and dominates minus norm of E. Second property, which will be crucial for us, lambda E equals absolute value of lambda times B of E for real lambda. In particular, this is an even function. 3, B is a Lipschitz function on E. I will skip this point because this is not that necessary to understand what is going on. And the main point, and which is most important for the next of the proof, is that the following inequality holds. B is smaller than integrate over B of E plus gradient phi of x dx for every phi from C0 infinity 0,1 to the power d. This property is called quasi-convexity sometimes, and this will be very crucial for our proof. So maybe let me shortly prove the first two statements and indicate how to prove the fourth. So the first is very easy. So that one, inequality, is obvious almost because we just plug function phi. Where is this function phi? Equals 0. And we just use the fact that this is the linear operator on finite dimensional space, so it must be bounded. And that's it. Opposite inequality is just a little bit more difficult. Let me write it down. We use triangle inequality for that. J equal 2 to m. Where is that? Tj, I just plug the definition. Minus c times t1 of e plus phi. Yes, this is what I have to calculate. Now, just triangle inequality with minus here. So I repeat this, j equal 2 to m t, I should put tilde here, yes. E plus gradient phi minus t1 of just gradient phi, c here, minus c, yeah, that's it. T1 of, so this is the, t is the linear operator, so I can use the triangle inequality, but because it's minus, so inversely, yeah, E. Now I use the fact that this is dominated by other elements, so let me, in the integral, so I put here equal to the power m t of E plus gradient phi minus c. No, not c is not necessary here, yeah? Well, let me check it. C is not necessary because c is just the constant of domination. So this is the point, sum of t j of gradient phi, yeah, minus c t1 of e. Now I use the triangle inequality again, and I get here, let's say, no, now it's equation, just sum of j equal 2 to power m tj of e plus gradient phi minus tj of gradient phi, oops, minus c t of e. And now I use the triangle inequality, so this disappeared, and I have that this is bigger than, so if phi disappeared, then this, we don't need the integral because it's not variable function, and we have that sum of t tilde e minus c t tilde e, okay, and this is minus, and this is obviously at the same point that it was bigger than minus, let me see, minus, I make something, this is smaller than, this is bigger than minus e, yeah, something like that. Maybe I skip this, this type of calculation, which is not really, yep. Yep.
If phi, let's see, where are we integrating? Are we integrating?
Yes, we're integrating over Rd, but the function is the function of parameter. Parameter here is this vector space.
So if we're integrating over Rd, over most of Rd,
is 0, because outside, you see this function is 0 outside the...
Right. So what about, so what would v of, so what is v of e? V of e had better be 0, otherwise this integral will diverge. Integral on the cube. Wait, that was the integral.
Yeah, okay. So maybe, yes, maybe I should write it really explicitly that we are integrating over the cube. I mean, yeah, that's too fast. Okay, so the next step, I mean, the first property is easy, but the second is more useful, and it's almost obvious why it is so, because by the definition, b of lambda is nothing but the infimum over, maybe I will write it down precisely at that moment, of the integral of v lambda a plus this gradient of phi of x. Yeah? But now we can plug the lambda outside because v is like linear or absolute value of linear, so we can write it down that this is equals this infimum over the same times absolute value of lambda times v of e, and here we put plus gradient of lambda to the power minus 1 phi of x. This is just multiplication by constant. But you see that this function belongs to the same set. So this is nothing but just that number lambda times v of phi, and that's it. Yeah? So this was easy. And the third is relatively trivial, and I skip this because it's not needed. The essential one is the fourth property. So let me show you how we prove this. So fix for a moment phi in C0 instead of 0,1 to the power d. And let's take the unit cube and divide the cube or many of small cubes qk. So this is the family of cubes, and k there is some set of parameters, and they are very small. How small you will see in a minute. And okay, first of all, this will be so small that the function phi restricted to qk is almost constant. Then we take a function of, let's define any function, any set, any collection of function phi k. So to every cube we connect one function phi k, which will be phi k will be the function in, for every k will be the function from C01 on, infinity 01 to the power d, okay? And so phi tilde here, and the rescaling we call phi without tilde, the rescaling of those functions. So it will be the function of the form, let's say, lambda to the power minus 1 times phi k of x minus y times lambda when y is 1 is chosen in such a way that the qk is passing by the linear, by the affine change of variable to all the cube 0,1 to the power d. So this would easily achieved. So having that, we can write that okay, the alpha of phi k of x. Okay, maybe I take a mistake. I should put minus m here, which would be better adjust to the level of my differentiation. So remembering that alpha has rank m, we get this is nothing but the alpha of phi in point x minus y times lambda. So now we can calculate b of e, which is the integral over 0,1 to the power d, let's say v of e plus, and now maybe it's smaller, let's say, sum of gradient of phi k, I will explain in a minute, of x from k, okay, k are going over all those cubes, plus gradient of phi of x. So, okay, so those functions are zero outside their cubes and they're in C infinity, so we can plug it in the definition of function b as in one of those functions over, which is here, okay? So we add any of those functions, and all those, this function here is big function is still from that family function which are allowed to my ass. Now, oops. What we do next? What we do next? Next we do nothing. We just say that this is sum over k, the integrals over qk of v of e plus function of psi k of x. Look that here, in the cube qk, only one function exists, other are zero, so I can just put just this one function phi k plus, and here I have some unfortunate piece which is not C0 on my cube, but nevertheless remember that this is almost constant. So I write it down that, so maybe I can write it down that this is, okay, let's do with that. This is nothing but integral over VE plus gradient of phi psi k of x plus gradient of phi in some point vk, which is some point of q, because this is function. Okay, this is not equal, but almost, and we can approximate this. Then it's further equal. The integral here is over qk. The integral over qk times v of e plus gradient of phi k tilde of x minus y times lambda plus, here I did nothing, just plug the definition, but now I change the variables, and this became nothing but the measure of qk times the integral over 0, 1 to the power d v of e plus gradient of psi k tilde of x plus gradient of phi of vk. Here we have still the constant point. So here we have this absolute value of the Jacobi matrix, and then I need more space. Maybe I use that blackboard again, because now if we sum all those expressions over the k, as it is indicated in the beginning, what we get that b of e is smaller than sum of integral over k, integral over qk, b of e plus what is written here? Phi of I'm sorry. Wait a minute. This, what is written here, you see, this is now a constant function. So this is a kind of vector here, because this was a gradient. So this is, let me put once again, times the integral over 0, 1. And here we have v of e plus those gradient. This is, no, this is b. No, this is without the integral. This is just the definition of b of e plus gradient phi of vk. Yeah, I mean, this is not the definition of that. But if we choose the function psi to almost satisfy this infimum, we have just almost equation here. So now, if we sum all those expressions, yeah, if we sum, so what we get, sum of those things, let's say, phi k times the volume of qk. So what you recognize here is nothing but the Riemann the approximation of the Riemann integral, which is what we wanted to do, yeah? Up to epsilon, but we do everything up to epsilon, and this is how we prove this property. Okay, so the first part is over. Now let me go to the second part of the proof. I can erase this probably. No, maybe that one. So you see that this is kind of this quasi-convexity, this is kind of convexity. But this is, quite functional convexity, it's very difficult to work with that. We want to replace this by other convexity, which is easier. So what we do now is we try to prove some other convexity of those functions. So for that reason, I introduce something which usually is called rank 1 convexity, but don't be so nervous about that. This will be much simpler. So the expression I will write down in a minute doesn't explain the name, but this is that simple, yeah? So let's call the vector of the form EP equal p to the power alpha times E alpha, where p is an element of Rd. So this is just the usual thing. Let's call this generalized rank 1 vector. It's very hard to explain why this is that name, but believe me, it fits to this. This was just made for presentation to be obvious. So the next property is the following. It will be the theorem that B is convex in directions of EP for every P. Okay? So this is the line, and in any of those directions, the phi is convex. So now, why it is enough for our purpose? So suppose we know this, that we already have this theorem, the second theorem. So why it follows that B is actually positive? Okay. So it is not a difficult task to find a collection P1, P, let's say capital N, or maybe shorter one, such that span of all those elements, E, P, J, are all our space E. I mean, there is a lot of freedom among them, such. Okay, so now we plug the following function, phi of Z1, Z, how many is those vectors? Zn will be B of sum of Zk E Pk. So immediately from the definition you get that function phi f is convex with respect to any coordinate. So it's coordinate-wise convex. Moreover, it's homogeneous of degree 1, and it's even function. And we use the following next lemma, which I skip, and I give you as an exercise. Lemma that wherever f is coordinate-wise convex, f of lambda x equal lambda f of x, then f is positive. So this is a nice exercise, by the way, and I will be back in that property because when I discuss what we can do, what we couldn't do. No, actually, yes, I think, yes. No. I mean, function B, in fact, is convex, but these are too weak to prove the convexity of function. Let me. I will formulate the problem later, which be about that, but let me proceed with the proof. So you will see that I have to prove only that the Maurer function B is convex in direction of those specially chosen vectors. Okay? So now it will be a kind of cheating. Okay? Because we take a function phi of x equal cosine of sum of p j x j from j equal 1 to d. Okay? And I would like to plug those functions in the definition of B. So you immediately recognize that it's not actually not fit those definitions because it's not C0. But now I'll try to convince you that it is not a big deal. I mean, what we do with those functions in real proof, we take kind of modifier which is 1 very close to the boundary of the square and 0 outside, like that. And let's denote those functions phi. And we consider the function of the form phi of x, let's say, let me put in that way, tau to the power minus m phi of x tau times phi of t tau x. So when this is those function phi. So if you work a little, this is very standard, you will show that everything which I prove with phi could be done with that function, so up to some epsilon. So the actual algorithm is that first you choose your epsilon here as small as you wish, and then you choose a very big parameter t, which allows you to kill all the remainings here. This is, I mean, this is no way on the lecture to prove this, but this is. So, having this in mind, so believe me that I could plug this function in the definition and it works. And up to some epsilon it works, and what you do actually is the same what I will do with that function. So this is kind of element of cheating on the lecture, but without that it would be much more or less clear what I'm doing. Okay, maybe let me work a little here. So this is a nice idea to use that function, because this specific function makes the proof so nice and so easy. So probably this is the main. Oops, where is my? So, actually, we differentiate those functions, yeah? And so what we get that the alpha of cosine of sum of pj xj is nothing but p to the power alpha times the alpha of cosine, yeah? Because this was linear function times p j xj. Okay, when this is the derivative of cosine. Now, we are very lucky because I present the proof in the situation when we are in the isotropic situation. So every number here is the same. So let's suppose that this is divisible by 4. So what we get is that if I call those function phi, I already called it, that the gradient of function phi is nothing but cosine of sum of pi xi times EP. Remember that the coordinates of the A alpha was p to the power alpha.
Cosine or sine?
You can be, okay, cosine, I said divisible by 4, I mean, yeah, but if it's divisible by 2, we put minus 1, and otherwise sine, this doesn't matter, I mean, just for example. Yeah, so, okay, so, B of A is smaller than, of course this is smaller because the B of A is infimum of those expressions, and we just use the one of them, integral of B of E plus gradient, and we multiply this function by additional parameter lambda, which will be, you will see for what in a moment, phi of x, yeah, the x, so this. You remember the discussion I made before. Actually, we plug this function, but it will be too big mess on the blackboard just for the simple reason that I kill one epsilon. So what is this? This is nothing but, as I said, integral over 0, 1 to the power d of b times e plus lambda, let's say, cosine sum pj xj times ep dx, yeah? And now there is a nice, very nice trick. You see, because what I said, that this is nothing but integral from 0, 1 to 1 be plus lambda times cosine 2 pi t ep dt. Why it is so? I change the integration. Because, you see, because the function, let me give some place here. Huh? The function cosine sum pi xi is equimeasurable with the measure, the x on this box, on this cube, is equimeasurable with function cosine 2 pi t dt on 0, 1. So I can change the integration by this simple one. So this is a very nice trick which allows me to go further. And I go further. You see, I introduce just for a while. Okay, so you remember what was here. I introduce just for a while a function, let's say k of s equals b of e plus s times ep. This is the definition, okay? So it is what I wrote a minute before is that this is smaller than e plus s ep plus lambda cosine, here is integral from 0 to 1, 2 pi t times ep, yeah, dt. Just I calculate the b in that vector, in that point, yeah. And this is nothing but, you see, I go with the vectors ep out of brackets. This is so simple. E plus s plus lambda cosine 2 pi t times ep, yeah, dt. And this is nothing but the integral from 0 to 1 k of s plus lambda cosine 2 pi t, yeah? Just by definition of k of s. I did nothing. And now I have a very nice situation because I'm in the function of one variable which has this special property that the function is smaller than the average of those functions which is perturbed by the cosine with arbitrary lambda. And now this is almost the end of the story. I need just one lemma more. Lemma, if chi is like as above, let's say, then k is convex. So let me prove this. Okay, take the test function phi in C 0 infinity of R, which is positive. And let's make a kind of distributional calculation, which will be easier. Integral over R, k of x times phi of x dx equals, now it's smaller than the integral over R, the integral from 0 to 1. We now plug the definition, our assumption, k of s plus lambda cosine 2 pi t, yep, times phi of x dt dx. We go with this perturbation to x now, equals integral over R, integral from 0 to 1, k of x and phi of x minus lambda cosine 2 pi t dt dx. What we do now? This is a test function, so this is smooth, so we can write down the Taylor polynomial for the Taylor x. But I have no. Oh, okay. I go here. Okay. Taylor expansion of rank 2, I think. Yeah, it should be enough. So it is like, okay, integral over r, integral from 0 to 1, and here we have, here is k of x, and here we have phi of x. So our we have the Taylor series in point S with respect to the parameter which is here. So phi of x plus, what is here, lambda cosine 2 pi of t phi prime of x, yeah, plus lambda square over 2 times cosine square 2 pi t phi bis of x. And now there is some reminder, which is O small of lambda dt dx. So you can immediately see that something disappears. What disappears? Yeah, cosine disappear. We integrate over 0 to p with very fast oscillating functions. So this disappear. And what we get, it is that this is equals integral over, okay, if this disappear, you see, we have that expression is smaller than that one. So this also is cancelled. So what we get finally, we get that 0 is smaller than 1/2, let's say, the integral cosine square 2 pi t dt times integral k of x times phi bis of x plus O lambda square divided by lambda square. Yep, yeah, you get with that. So what does it mean? That this is positive. And what does it mean? This doesn't mean that k bis times phi is bigger than 0 for every positive phi which is test function, which means that k is a convex function, and that's it. So, so this is how the proof looks like, and I believe that it was accessible up to some cheating inside. Now, just few comments. So one comment was about this anisotropic case. So everything goes very smoothly as it is, provided we can plug the function cosine. You remember when I differentiate, I said, okay, every alpha is divisible by 4, so I can put cosine everywhere and so on. But this is not the case when I have mixed derivative. It depends. So in the case when the rank of every derivatives in our polynomials is even or every is odd, it works the same way, believe me. The problem appears at the moment when I have even derivatives and odd derivatives on my hyperplane. And then everything I could say, I could proceed with the same procedure, but with one exception. I couldn't prove that my function is coordinate-wise convex. I only can prove the following, not prove, I only can achieve the situation that I have some function with the following property. This is a function of the even number of variables then. It will be z1, z2, z3, let's say z4, z2k, such that when I take the consecutive pairs and I fix any variables outside any pairs, I get a function of two variables. And I can prove that my function is subharmonic with respect to those variables. And this is one homogeneous, and this is even. And then there is a question which we couldn't answer. Is it enough for the function to be non-negative? So I formulate this as an open problem now. Be careful. If it is just function of two variables, we can prove this. So if this is a function of three variables, and instead of assuming that this is subharmonic over 2, I assume that this is subharmonic over 3 variables, it is not true. I mean, there exists function which is subharmonic with three variables, which is one homogeneous, which is even, and it could be negative. So there are mixed evidence what can happen, and so probably I asked everybody. Nobody knows how it is. So, but this is a really nice problem which deserves to be solved. I mean, and this problem really will give a final solution of this Ornstein problem. And well, maybe I finish because this was complicated. Thank you.